Assalamualaikum warahmatullahi wabarakatuh and very good afternoon. We are from umbrella.co group 14. We will assign to do a solution 5.35 question 5.35. So the question is a gas turbine power plant receive a shipment of hydrocarbon fuel whose composition is uncertain but may be represented by the expression CXHY. The fuel is burned with excess air, and analysis of the product gas give the following result on a moisture-free basis: 10.5% CO2, 5.3 O2, and 84.2% N2. The question is A. Determine the molar ratio of hydrogen to carbon in the fuel, where R equal to Y over X and the percentage excess air used in the combustion. Second, what is the air to fuel ratio, meter cube air over kilogram of fuel, if the air is fed to the power plant at 30 degrees Celsius and 98 kilopascal. So I will show the solution. So move on to so based on the information that given, so we will make a basis. At product we will have a basis of 100 kilomole dry gas. So basically I will sketch a full diagram of the BFD. So for the first stream is the fuel, which is N1 kilomole. So we don't know how many carbon in the fuel component with the hydrogen as well, so we denote it as CXHY with M1 as a mass of the fuel, same as well. And then the product gas with the basis we assume 100 kilomole dry gas with the information that given in the question, which is 105 kilomole CO2 per kilomole dry gas, 0.050 kilomole O2 per kilomole dry gas, 0.8043 kilomole N2 per kilomole dry gas with unknown water we denote as N3 kilomole H2O per kilomole. Alright, so for the this is third string, this is first string, so this will be second string, where this is for the air. For stream number 2 we don't know the mole of air, so we denote it as N2 with the general composition of air, which is 0.21 kilomole O2 over kilomole air with 0.79 kilomole nitrogen over kilomole air. And then we given in the question the information of the temperature and pressure, so we can find volume while using the ideal gas. We denote it as V2 as in meter cube. So this is complete diagram. Okay, so right now we already know that the unreactive species is nitrogen because it didn't react from input to the output. So we do the nitrogen balance, which is N2 kilomole N2 times with 0.9 kilomole nitrogen gas over kilomole air equal to 100 kilomole dry gas time with 0.84.3. So we will know the value of kilomole air into the input. So the N2 is I'm sorry, I think the information is supposed to be 0.842, which is not 3. So we change the value. .2. So the mole that enter the mole of air that enter this process unit is under 6.58 kilomole air. So we know the value of N2. So now we can determine the value of kilomole H2O, which is we can do the atomic species balance. So in this unit, the reaction occur is where the fuel CxH1 plus O2 gets CO2 plus H2O, which means that the independent atomic balance, the atom that used in the reaction is C, H and O. So we can do the O balance where in air, in the input we found O oxygen atom in the air, so 106.58 times with 0.21 kilomole O2 over kilomole air, and then times with how many oxygen atom in the oxygen molecule, so 2. So time with 2, because oxygen molecule have 2 atom of oxygen equal to 100 kilomole of the product time with 0.05 kilomole CO2, and then time with how many oxygen atom in CO2 molecule, which is 2 O2 in 1 CO2. I'm sorry, it's not O2, it's atom of oxygen. And then plus with 100 kilomole times with 0.053 O2, and then how many, and then times with 2 oxygen over 1 O2, and then plus with N3 kilomole H2O, and then times with plus with N3 times with N3 is kilomole H2O, and then time with how many atoms of oxygen presented in H2O molecule, which is 1 O2 over 1 H2O. So we calculated the answer. This is 44.76. So so 100 Alright, So this is 31.6 plus N3. So N3 equal to 13.16 kilomole H2O. So now we already know the N3 value, which is equal to 13.16 kilomole H2O. So we can do the C balance to know how many fuel that injected. So the solution is N1, which is we don't know the kilomole fuel, kilomole CXHY times with 1 kilomole CXHY, and then how many carbon atom that presented in fuel we denoted as S because we don't know kilomole C, and then equal to the product, and then equal to the output, which is found in dry gas, 100 mole kilomole dry gas times with 1 kilomole dry gas with 105 kilomole CO2, and then we calculated, we got this N1X. So we can do the H balance, which is N1 kilomole CXHY times with Y, because we don't know how many hydrogen atom in the fuel, so we noted as Y, kilomole hydrogen, over 1 kilomole CXHY equal to 13.16, which is the mole of H2O times with 2 kilomole H over 1 kilomole H2O. So the answer is supposed to be N1 equal to 26.32. So we want to know the ratio of H over carbon, which is we want to divide this equation 2 with equation 1. So N1Y is for the hydrogen over N1X is for the carbon, which is N1, which is for the N1Y equal to 26.32 over N1X for the carbon 10.5. So we can cancel this unit because this one same. We calculated this, so we get 2.51 kilomole H over kilomole C. So we answer the question for the first part of the question. Now for the second part, we want to know the percentage excess air. So in the question also, we know the O2 feed, which is 0.1. It's supposed to be 106.6 kilomole air times with the composition of air or the composition of oxygen in air, which is 0.21 kilomole O2 over 1 kilomole air equal to 22.4 kilomole O2. And for the O2 And for the O2 product, which is 100 kilomole dry gas time with 1 kilomole dry gas per 0.053 kilomole O2, which is equal to 5.3 kilomole O2. So based on this feed, O2 feed and O2 product, we know that there's a difference, and that difference is a O2 theoretical. So O2 theoretical, that where the O2 theoretical is used to produce CO2 and H2O based on the amount of fuel. So the difference is the feed minus the product of O2. So we get 17.1 kilomole O2. So we change this O2 to find the air theoretical, which is 7.1 kilomole O2, 0.21 kilomole O2 times with 1 kilomole air. So we can cancel this. So the air theoretical, which is how many air that consumed, is 81.43 kilomole air. So we now know air theoretical, so we can determine the percentage air excess, which is the question given, which is air fed minus air theoretical with air theoretical times with 100. So the air feed, based on the calculation, is 106.6 kilomole air minus the air theoretical, which is 81.43 kilomole air, over the air theoretical 81.43 times with 100. So the answer is 30.9, which is approximate to 31%. So that is the answer that's the answer for the second part of the question A. So now we will move on to the question B, which is the question asks us to find the air to fuel ratio, which is the air supposed to be in meter cube while the fuel supposed to be in kilogram. So for this kind of question, we have to use the ideal gas law. So in the calculation, we already know the air mole of air. So we use P. So the pressure for the second stream P2 is 98 kilopascal, and for the temperature, we do not, the ST2 is 30 degrees Celsius, with N2 is the mole of air feed, which is 106.6 kilomole air. We want to know the V2, the volume of air in meter cube. So we use the PV and RT gas and other gas law, and then we simplify the equation. Okay, I will show this one. I will show you another way. The other gas, we can divide it with standard temperature. We divide it with other gas that use the standard STP, which is standard temperature pressure. So this is PS, which is standard pressure, which is specific molar volume is denoted as V, and okay, like that, and then RTS. So we can cut this value because this is the same, and then we simplify our equation because we want to find volume at stream 2, which is V2 N2 GS PS. No, this one is T2, specific molar volume, over pressure 2, temperature stream 2. No, temperature standard temperature. So we put our numbers. For N2 is 106.6 kilomole air times with temperature stream 2, which is in 30 degrees Celsius. We have to change it into Kelvin, plus 273 Kelvin, over 98 kilopascal, which is pressure for stream number 2, and the time with standard pressure, which is the general is kilopascal, 101.3 kilopascal, over the standard temperature, which is 273 Kelvin, time with the specific molar volume, which is 22.4 meter cube, over kilomole. So we can cancel this unit. No, this one can cancel. Sorry. Okay, this one can cancel. So calculate this. So the answer is 2739.48 meter cube, which is approximate to 2742 meter cube. Okay, so this is volume for the air. So now we will find the mass of the fuel, which is at the first stream. It is denoted as M1 kilogram. So M1 kilogram is equal to, as we get the as we know, the carbon, the total carbon is N1X according to the solution that we already did, time with the atomic weight of the carbon, which is 12 kilogram carbon over 1 kilomole C. So we can cancel this, plus total amount of hydrogen atom, which is N1Y kilomole H, time with the atomic weight of the hydrogen, which is 1 kilogram H, over 1 kilomole C H. So we can cancel this. So the answer, for the N1X, we already know the value of the N1X, which is, for the N1X, total carbon atom, which is equal to 10.5 kilomole C, and for the hydrogen atom, the total is kilomole hydrogen. So I forgot. Alright, so this is 10.5 times with 12 plus 26.32 times with 1. So we calculated this. Okay, so the answer is 152.6 kilogram. So now we can determine the ratio of air, which is in volume, over mass of the fuel, which is in kilogram. So Volume is 2743 meter cube air over 152.6 kilogram fuel, which is the ratio is 18.0 meter cube air over 1 kilogram fuel. So this is the solution for the question B. So that's all for the solution. So this is all of this are the answer. So that's all. Thank you.